Yeah, okay. So this is going to be a topic preview for 5G cellular networks. Now 5G cellular is a huge area of research. It spans everything from physical layer to the networking layer to the applications. So what I will try to do here is just give a very brief introduction as to what has been going on in this space through standardization. And just touch upon some of the research areas that are still open for new research to be done. So my name is Monisha Ghosh. I'm at the National Science Foundation in the US. I'm also with University of Chicago as a research professor. Today I am giving you my viewpoints, not on behalf of NSF. Sometimes I will put on my NSF hat, but most of the time these are my opinions and my viewpoint, not speaking for NSF here. So a brief, it's always good to see how we got somewhere from wherever we started. So if you go back and look at what has been now almost 40 years of cellular, it doesn't seem that long, but a lot has happened. Your 1G system started off in 1980, and that was really only analog voice. It was circuit switched voice. And actually 1G was never called 1G until 2G came along, because there never was any intention that nobody planned this evolution of the Gs going all the way from 1 to 5. So when 2G came along in 1990 was when people went back and labeled 1G as 1G, right? 2G was really more about digital voice. That's where you had CDMA come in, GSM come in, circuit switched voice and data as well, but data was still circuit switched at that time. So you had systems like Edge, GPRS, which sort of were 2.5, 2.75G, and that took you to 3G, which was quite a departure from the previous systems, because the data was now package switched. Voice still remained circuit switched, but this was really the first system that was designed more for data than voice. And this was the first stage that customers got of what it would be like to have mobile data, right? And that led into 4G, which really was the first true mobile broadband system using OFDMA, and now you had packet switched voice and data. And now we are looking at 5G, which is supposed to roll out soon. And the new thing, the really new thing that's happening there is millimeter wave. So people look at Gs in different ways. The one that I was talking about was circuit switched, was packet switched. But it's also been very much focused on what is the physical layer technology that was used, right? So you went from analog to digital, and in digital you went from TDMA to CDMA to OFDMA. In 5G, we have not made drastic changes in what the physical layer looks like. It's still OFDMA, it's still packet switched, and the new piece is that we are using new spectrum. I don't know how many of you have seen this picture before. This is an iconic picture which sort of captures very well as to how the impact that smartphones and mobile data has had on our lives. These are two pictures taken during the inauguration of the two popes, one in 2005, one in 2013. And this was an article that appeared in the New York Daily News in 2013. And this is the difference that technology has brought to us. In 2005, you have one little, it's not a smartphone, it's a flip phone with a screen there. That's all you can see. And in 2013, the picture has completely changed. Everybody has their phones out to record what's going on. And this has really been, that was the 3G to 4G transition that we're talking about. If I go back a little bit, the other thing you'll notice from here is that it's more or give or take a couple of years, it's about 10 years between generations. And usually as one generation is just beginning to mature is when the research starts on the next generation. So I remember back in 2000, I used to work at a company called Philips back then, And we had internal discussions as to what 4G is going to look like. So if we are looking at 5G rolling out now, we as researchers, we should already be thinking about what is beyond. You know, what are the potential limitations? What is the things that 5G cannot do that are going to be done next? So these are the 5G use cases, requirements, and technologies. So on this side, you've probably seen these applications time and time again. So it's basically broadband access everywhere, high user mobility. We're looking at high-speed train usage. You have the massive Internet of Things, the smart city kind of applications, the extreme real-time communications, which is very, very low latency, giving you the tactile internet, disaster communications, e-health. We heard the ministers talk in the morning about how all of these e-health services are going to become more important, and then broadcast services as well. And on the right, you see some of the numbers behind these use cases. The user experience data rates are going to go up. The minimum people are shooting for is 100 megabits per second, going all the way up to 20 gigabits per second peak rates. Pedestrian, 200 kilometers per hour mobilities. The cell age data rate, and that is actually one of the biggest limitations that you have in today's cellular networks, is you can get very high throughput if you're really close to the base station, but as you go towards the cell edge, your throughput drops off. So having that as a performance metric is very important. Latency, the requirement is of having 1 milliseconds latency, which is, and today we are at about 15 milliseconds, so that's a huge reduction that is going to be given by 5G. Connection densities are going to go up, and this is more for the smart city, Internet of Things kind of applications. Energy efficiency is not something we talk about a lot, but that is also one of the performance metrics for 5G to hit. And then spectrum efficiency, which is the one as communication network researchers we're more familiar with, and there we want to get to 10 bits per second per hertz. So if you look at the standard Shannon capacity equation down there, right? Capacity as a function of bandwidth, A is the number of antennas, and signal to noise ratio. So you really have only 3 parameters that you can play with to increase your per link throughput. And all of these are going to get hit in 5G, right? So A, which is in red, number of antennas, is what massive MIMO is going to tackle, the degrees of freedom that you can get. The B is which is the bandwidth. We're running out of bandwidth in the low to mid-range frequencies. That is what millimeter wave is going to give us. We're going to get the larger bandwidths in millimeter wave. And the signal to noise ratio, basically you keep the signal to noise ratio high, but by making sure your deployments are small cells. So you basically artificially limit how low your signal to noise ratio is going to be before you hand off to another small cell. So in terms of where we are on the physical layer with 5G, we are pretty much hitting all the 3 knobs that we have in the capacity equation. So let's look at spectrum a bit. This is a chart of the United States, frequency allocations going all the way from baseband to all the way up to terahertz and beyond. And if you look at the 60 gigahertz spectrum, which is that little circle over there, that is the 60 gigahertz unlicensed spectrum. The spectrum that is available there today, which is about 14 gigahertz, is equivalent to all of the spectrum that we have for commercial services below that. So it tells you that we have achieved a huge amount of communication capability given the spectrum that was allocated in the lower bands. But to really push it forward, we have to look for new spectrum. And millimeter wave is where you have clean spectrum. That, when I say clean, I mean it's not already allocated to other services. I will talk later about other places, other actions that, at least in the US, the FCC is taking to make more spectrum available in the lower band. Of course, the problem is, as we all know, is as you go up in frequency, your propagation goes down, and you have a lot of other problems that you have to face. But those are technical problems that researchers have been working on for many, many decades now, actually. Millimeter wave The first millimeter wave systems that came out were the wireless PAN systems. And now to imagine that we've gone from millimeter wave transmission over literally inches to 200 meters, it tells you how far we've come in terms of what device technology can do, what antenna technology can do. And they're really, I mean, this pace of innovation is just going to continue. So let's look at this. I will take with a grain of salt because this is coming from a trade magazine whose job is to have all the curves go upwards. But these are good pictures to keep in mind. So if you look, we talk a lot about 5G, but if you look at the projections, even at 2021, it's really going to be 1.5% of all data is going to go over a 5G network. So there is a huge lag time that it takes for something to get deployed and for it to get widely used. The other interesting thing about these projections is that 4G is not going to stop. You know, the 4G growth is going to continue. And even the way the standards are written, the first 5G systems are going to be not standalone, so what they call NSA. So they are going to, you're going to have a low band and a high band millimeter wave 5G as well. Of course, 5G NR has both aspects, low band and millimeter wave, but the thing to keep in mind is it's not a sharp drop-off. So a lot of innovation that has happened in 4G standards all the way up to release 13, a lot of that has yet to be implemented and rolled out, and that is also going to continue in parallel with 5G. Another projection which I find very interesting to look at, this does not have specific 5G projections on it, but this is talking about very specifically machine-to-machine communications, data going over machine-to-machine links, whereas the previous one was over all kinds of transmissions. So today, which is the curve, I guess, maybe more 2018, you'll see that if you look at the percentage of machine-to-machine traffic, that's the highest percentage is actually going over 3G. So what is happening today is that the 2G and 3G deployments, the networks are out there. People are not using them for high data rate applications. And they are being repurposed already for the machine-to-machine kind of application. So today, most machine-to-machine communications is happening over those systems. And that is going to continue for a while. So even though the data traffic, the high bandwidth data traffic is not going to die, is going to die out, the M2M traffic is going to continue at a fairly steady pace all the way up to 2021 as your 4G and 4G plus traffic keeps up. The other interesting thing is to look at the green line. That is LPWA, which is low power wireless LAN. So there is this whole host of other systems out there that also do machine-to-machine over long distance pretty well. You have systems like LoRa, you have systems like proprietary systems like Sigfox that are also getting traction in the marketplace. So we have to take all the projections that 5G claims that they are going to be the IoT standard with some grains of salt. There are other systems out there that can also perform that same role. So what are some of the 5G services that one can expect? So if you look at most 5G presentations, if you look at 3GPP, they've broken it down into three major categories. One is enhanced mobile broadband. That is the one that we're all most familiar with, which is basically, let's increase network capacity, let's increase the higher peak data rate. So that is the one that the capacity equation goes after. And the applications are basically data intensive, those which require large bandwidth, video streaming, immersive gaming, the ones that have these very, very high demands on traffic. The next bucket of services is going to be what's called ultra-reliable and low-latency communications, or URLLC. And the key performance indicators for that are kind of different from what it is for eMBB, which is, and that is high reliability and low latency. So data rate is not the main driver here. What we want is, I don't know, 5 to 6 nines availability and extremely low latency of the order of 1 milliseconds. And the applications that people are talking about for this kind of a service is real-time control, what's been called a lot as the tactile internet, where you really almost can have a real-time control with applications that are very far from you. Autonomous driving is another application that will require this kind of very high reliability and very low latency services. And the third one we touched upon a little bit already is the massive machine type communications, when here the key performance indicators, the KPIs, are connection density and energy efficiency. So sometimes some of these applications, like in smart cities, you want to have a bunch of sensors out there, and you want the batteries to last maybe 10 years. And the challenge is, can a cellular system provide that kind of energy efficiency for these devices? So most of the applications fit into this pyramid. And there's a reason that they've put enhanced mobile broadband on the top of the pyramid and not at the bottom, because that is still the biggest driver. So for example, millimeter wave is what is going to give you that high data rate service. The applications sort of fall within the triangle. So if you're going from really high data rate to machine type communications, things like smart cities, smart homes with cameras and videos on them, for that it's still, it's still device to device, it's not device to person. But the data rate requirements are going up if you're transmitting camera feeds throughout a building. If you go down the other side of the triangle, from enhanced mobile broadband to ultra-reliable and low latency, for example, self-driving cars are right now over there, but you can imagine that would move up that side if now your sensors are more video, and it's not just telling you what speed you're going at and how far and what direction you're going at. But the other applications on that side are really what are familiar to us: 3D video, ultra-high definition, cloud access would require, the enhanced mobile broadband, and depending on the application, you probably also want low latency in there. Industry automation is a big growing segment now, and there is this trend now, actually in Europe and many places, where a big factory can sort of have their own spectrum and deploy a cellular system just in the factory floor that does industry automation for them. And then, of course, there is voice, which is reducing in importance as we go off our phones. We barely talk on our phones anymore these days, right? This is the vision. Now, keep in mind that I'm fairly sure that there will be applications that come out once 5G really gets deployed that none of us in this room are even thinking of. Think about something like ride-hailing services like Uber, right? 4G is what actually enabled that whole thing to go off. We don't think about it as much, but the first precursor, I think there was a small company that came up with a similar service, but at that point you just had 3G, and it was very, very difficult to make that application work on 3G. So these are what we know today. What we don't know today, we will come to know in 10 years as to what 5G will enable. And that is why whenever people talk about things like what is the killer app for 5G cellular networks, it's, you can't design a network for a killer app. The killer app will usually follow once you have the network in place. So this is a chart on the timeline for 3GPP. So release 15 is basically the one that they came out in the middle of the year, somewhere in there, which completed the definition of both the standalone and the non-standalone parts of the 5G new radio. The release 16 study phase has already started, and I will talk later about some of the things that they're looking in release 16. And that, for 3GPP, they do this overlapping thing. As one standard as one phase, one release is winding down, they're already starting the study phases for the future releases. And right now, the vision is to have release 16 finish at the end of 2019, at which point it's probably, you can say that the 5G standardization will be done. So there's still time, a fair amount of time before the standard is complete. So what are some of the technologies that have actually gone into 5G? There was a lot of debate, a lot of research, a lot of evaluations on alternative waveforms instead of OFDM. There was FBMC, there was general OFDM, there was very, very active research area for a while. But at the end of the day, it's a trade-off. When you're picking a waveform, yes, there are certain situations where a new waveform might work better than OFDM, but then when you take it in the totality of all the different environments that you're going to deploy this in, it turned out that OFDM was still good enough in many ways. But they did change the way they designed the OFDM. It is more flexible, the framing. It has a scalable TTI, the transmission time interval, and that was done to meet latency requirements. It is also, the OFDM design itself is scalable from the bands you're operating in. So millimeter wave OFDM, the numerology is different from the numerology in the mid-band, but it is still can be designed, the numbers are very related. You have massive MIMO at sub 6 gigahertz. So when I say massive MIMO, sometimes there's a lot of confusion as to what is millimeter wave beamforming and what's massive MIMO. When I say massive MIMO, I really mean that every antenna element has an A to D attached to it. So you can really do digital beamforming. So that is really going to be at sub 6 gigahertz. In millimeter wave, you're going to have what we traditionally call more beamforming, which is a large number of antenna elements, but fewer RF units. The coding changed. Turbo codes was what LTE used through 3G and 4G. However, LDPC codes, the low density parity check codes, have pretty much become the industry standard for Wi-Fi. And for 5G, they decided to make the change to LDPC codes for data. And they picked a new kind of code called polar codes for the control channel. And then some of the other things, in and of itself, they don't look like huge advances. In fact, if you look at this whole list of what actually went into 5G NR, it seems like each one of them taken individually, you could almost say it's incremental. It's nothing massively different here. It's when you put it all together in a system, along with the upper layers, along with the network slicing, the combined access and backhaul for millimeter wave, the network densification, the ability to aggregate spectrum across different bands, to do unlicensed operation as well, which is a fairly new thing. That is where you get the real power of the 5G cellular network. Individual pieces, they don't look that hot, but together, so it's really in a departure from previous Gs. 5G is really more of a system, evolution rather than an individual, any one technology, dominating. The only place where I think that is different is millimeter wave. So millimeter wave is really unique to 5G, did not exist in any of the other Gs. So this is just a picture of network slicing. I've just picked one of those things. And the concept, actually, the people are implementing, you can implement network slicing in 4G. There's nothing specific about 5G that makes network slicing unique to it. It's just that given all of the options that you have available for you for physical layer, it's going to make more efficient. The other thing is the verticals that people are beginning to look at as applications is what is going to drive network slicing a lot more. So if you're deploying an industrial IoT system, the slicing that you do for that application is going to be, for example, very different from what you would do for a video gaming application. And the 5G cellular network will enable you to tailor the way you slice to your application a lot better. So the spectrum is still a challenge, I think, for cellular. In the low band and mid band, there is not a whole lot of new spectrum. Those spectrum bands are very, very crowded. And most of the existing spectrum that's used for 3G is going to be refarmed for 5G. There is the 3.5 gigahertz in there, which is the CBRS band in the US, which people can be using for 5G deployment. But the really new spectrum is coming at the high band, which is greater than 24 gigahertz, where you're really going to get the extremely large bandwidths for high data rates. Now, very recently, like less than a week ago in the US, the Federal Communications Commission, the FCC, put out NPRM, which is a notice for proposed rulemaking for a new band, which is 5.925 and 7.125 gigahertz. So this is 1.2 gigahertz of spectrum, which is going to become available, but on an unlicensed basis. There are already a fair number of incumbents in those bands. These are mostly broadcast relay services. For example, when you have remote news gathering and a television truck shows up to relay news, live news, they have dedicated frequencies for them to transmit that feed back to their stations. And those frequencies fall in that band. The thing is, though, that those frequencies are not used all the time. They're not used everywhere in the country. And so there is a huge opportunity there for spectrum sharing. This has been an ongoing proceeding for a while. There's been a lot of comments that have come into the FCC about the pros and cons of getting rid of the incumbents in this band and making the whole band licensed so they can auction it off to cellular companies versus keeping it unlicensed. And I think the ultimate decision that they made was to keep it unlicensed. What I want to point out here is that just because it's unlicensed does not mean that your 5G and your cellular systems cannot be deployed there. What we've seen over the last 3 or 4 years is how LTE has moved into the so-called Wi-Fi band. It's not really the Wi-Fi band, it's the unlicensed band. Wi-Fi just happened to use it first. So this is a case where there's a lot of future work that can be done to make sure that whatever systems get designed for this new 6 gigahertz band, be it Wi-Fi or be it cellular, is that they get designed with the goal of coexistence from day one. So this is a green field for both systems. 5 gigahertz was always burdened by the fact that Wi-Fi was there first. So when LTE starts deploying there, they have to coexist with something that's already got an established base. Nobody has an established base inside 6 gigahertz yet. And whoever can design systems that coexist very well, not only with each other, but with primaries in that band, they're going to get access to huge amounts of spectrum. I won't go, I did have a set of slides for another presentation that I gave on the spectrum rules for this band. These are proposed rules, but if there's interest after this, we can discuss that a little bit more. But it has, I think, opened up a whole host of new research for the community to pursue. So let's look at what 3GPP is doing in release 16. There are actually 25 new study items being worked on. Now, not all of them will rise to the level of becoming part of the specification, but they're looking at everything from the higher level of multimedia priorities, vehicle to V2X. You hear a lot about cellular V2X. It's there in 5G, but I think release 16 is going to look at more the application layer. They're trying to expand 5G, the specification, to things like satellite access, UAVs. UAVs are becoming one of the things people are considering very, very seriously for applications like disaster networks. So if you already had a specification for UAVs that allowed them to use 5G base stations as hotspots, that makes the deployment of these systems a lot easier. Local area network support in 5G, convergence, positioning. The verticals that I talked about is quite an important driver for some of the items in release 16. There is still discussion about novel radio techniques. There's nothing to say that something is not going to come along tomorrow that is going to make OFDMA obsolete. Security is a big issue. 5G did do a lot of security enhancements, but that is something, especially as the application space continues to evolve, where now you're doing more and more things in the cloud. And yes, there is security layers that exist in the upper layers, but what can you make even the wireless layer more secure? Network slicing, streaming, these are just a few things that are still being worked on in Release 16. So in terms of where 5G is today, is, as you've seen in news items, there was India Mobile Congress like 2 days ago. There were talks yesterday in some of the workshops. There's plenty of trials across the globe in both the mid-band and millimeter wave. Mid-band is probably the first rollouts of actual installations, not trials, will probably be in mid-band. And fixed wireless is probably going to be the first deployment. But there's a lot of tests happening in millimeter wave. Millimeter wave UEs are being designed. As some of you may realize, a big problem with millimeter wave in handsets is where do the antennas go? How do you make sure that the way you hold your phone is not blocking the antennas? And most of the device manufacturers have prototypes of these devices. There's a lot of research work that's going on there. Spectrum harmonization efforts across the globe are still ongoing. Most countries have allocated some spectrum, but there's no real harmonized spectrum across the globe for 5G, especially in millimeter wave. The big thing that's happening over the last year, I would say, is research test beds being deployed in India. There was an announcement about less than 6 months ago about 5G test bed being deployed here. In the US, the National Science Foundation, along with a bunch of industry consortium members, are working hard to deploy test beds, and Europe too. And most of these are partnerships between industry and universities. And the biggest driver is, as you can imagine, given even the very brief overview that I've given, is how much more complicated a 5G network is compared to even what we had in 4G or 3G or 2G. And most of these standards have been designed on paper, right? So pretty much everything gets designed on the basis of simulations and analysis, and the standards bodies do a fairly good job of it, but the real proof of the pudding is when you go and deploy it. And for academic researchers, this last step is getting increasingly harder to do because of the complexity of these systems. So yes, maybe you can just demonstrate a physical layer improvement as a point-to-point improvement, and you can actually build something and show that. But does that translate into what's called area efficiency? It's not only bits per second per hertz, but it's bits per second per hertz per square kilometer. Does it translate into network efficiency when you have 1,000 users using this little improvement you've made? That is extremely hard to demonstrate given very small prototypes. So the objective of these research test beds is to enable that kind of demonstration for academics and also for industry, actually. It's not easy for industry to build research test beds of this caliber either. So big part of the support that's coming from industry is so that they enable academics to do this research, but they also enable themselves to test out new ideas. And so this is development that I'm really excited about, and I hope it leads to really good research as well as new system ideas. So the question that I hear a lot about is, especially many times in industry forums, is 5G research is done. And what I would say is the standard is done, but the standard, I used to do standardization before, and while I think the process is fairly good, it's not perfect. Many times you pick something to go into the standard, which may not be the best choice that you've made. And that's why you really need the research into real-world performance that hopefully the test beds will enable. This is very challenging, but this kind of unbiased comparison between different proposals or different things can only be done in academia. This is not something that you know, I don't know, is anybody from industry in this audience here, or maybe online? But, you know, a Samsung or an Ericsson or a Nokia, they will all have their pet, you know, patented ideas that they want to push into a standard, and that comparative evaluation does not happen much in the outside of academia. And of course, as I mentioned before, research into beyond 5G. As I said, with the previous generations, as one generation was beginning to be deployed, the research community is already thinking about what's next. So that should definitely be a focus as to where we are going next, building on where we are today. Some of the 5G research areas, which is 5G today and beyond, is really, for example, understand millimeter wave performance in real-world mobile environments. Mobility is really, really tough for millimeter wave still. So there are a lot of ideas out there as to how you do handoffs, how you do base station deployments. You know, handoffs have always been traditionally done to one base station. Do we go back to the idea of, you know, being soft connected to multiple base stations at a time and you just switch beams? So there are a lot of new ideas that can be used in this space. Network management is emerging as a huge research area. I mean, think about the complexity of what we've built in 5G. It's orders of magnitude higher than what we had in 4G with the different radios, with the different network slicing abilities. How do you manage this network? How do you optimize it? What are the knobs you tweak to make sure you have the best performance? That is a completely open greenfield research there. 5G in unlicensed and shared spectrum, and I talked about this a little bit, which is including the new 6 gigahertz band. Applications of AI, we are seeing a lot more of that kind of research come up, especially in optimizing the 5G network deployment. And the problem with that whole research area is, as you know, AI, machine learning, those fields have made huge advancements in areas where you've had access to very good data, right? We don't have an ImageNet of 5G yet. And that should, again, be a big push for the research community to start looking at ways of gathering, curating, and making data available to the research community at large. So many times, somebody has a research collaboration with the service provider, and they get access to data, but it's only for them. So that data never gets released to the broader community. You get the results of what they did with the data, but wouldn't it be so much more valuable as a research tool if that data were being made available? So there's a lot of challenges on doing that, but that is something I wish the community focuses on as an endeavor of getting data sets not just for themselves, for their own research, but in a form that's available for the community at large to use. And the last thing is, no matter how much hardware and real-life test beds you build, comprehensive software tools and software simulation platforms are still very important. So even today with the test beds that we are building, it is going to be very, very difficult, or it's going to be a long time before we can actually test, 1,000 nodes, mobile nodes using millimeter wave on the streets. It's just not going to happen in the near term, right? So if you really wanted to do research on those things, the next fallback is analysis and simulation. If you want to do simulation, I personally feel that that's a perfectly fine thing to do, but just make sure your simulations are realistic. So you've modeled a 5G cellular network the way it's supposed to operate, not an idealized 5G cellular network. And it takes a lot of effort to build these tools. It's not easy, and that's another area where I think industry and academia needs to come together. So to conclude, let me just go through the list of papers that we have in this particular MobiCom around this topic in the 5G cellular session. So the first one is resolving policy conflicts and multi-carrier cellular access. So this paper really talks about what are the challenges when today you really can't do that very well. You cannot hand off a call from a Sprint network to an AT&T network. But there are hooks in 5G that may allow you to do that. And this paper analyzes some policy conflicts in current networks when you're trying to do this kind of handoff between multi-carrier. Here is not multi-carrier OFDM, it's multi-carrier service provider, really should be the right term here. So this is really not specific to 5G. Some of the methodologies, the results that were done here would carry over to 5G. This is the next paper is ECHO. It's a distributed cellular core network. So basically, this is an interesting one where they've basically taken a software layer and tried to do the LTE evolved EPC's evolved packet core in a distributed fashion over a public cloud. Again, this paper itself is not specific to 5G, but definitely the ideas and the methodology can be evolved to 5G networks as well. This is an experience paper, and it's got a lot of really nice data about, they've gone and taken measurements of roaming in Europe. This is 3G and 4G. I guess in Europe now, there are no charges for roaming anymore. And what they've tried to study is what does that do to the performance of the network when that happens. How should I slice my network? And the reason I've bolded some of those words is those are the kind of things that would apply to 5G as well, in addition to what's being done in these papers specifically. This is, again, going back to network slicing. As I mentioned, network slicing, people are implementing it in 4G today. And this paper also, obviously, because nobody has access to 5G networks today. It's for 4G, but the results could be carried over to 5G as well. And the last paper is probably the one that is the most closest and specific to 5G, because they're really looking at this low latency requirement and looking at the reduced TTI in the specification and asking the question, as now I have this very small transmission time interval, how do I do my scheduling in that little time? And they are proposing to do a GPU-based design to do that, and this is quite specific to 5G NR. So hopefully, in the next MobiCom, there will be more papers and more research where people dig more into the 5G standard and come up with interesting research problems to solve there. So I'll stop here, and I'm happy to take any questions you might have. That's it.
What is the state of B2X communication in 5G? Is there any new modulation scheme we are thinking of, or are we relying on current modulation scheme, or anything in particular we are looking in that direction?
So again, the entire 5G NR on the radio is all based on OFDM. And it is a flexible framing structure, so even for V2X, it's still going to be OFDM. As I said, there was a lot of research and debate before the standard was specified as to what should be used. But in terms of modulation and coding, so that is the one piece where 5G is kind of, they've made a decision. That's not to say that the research on new modulations cannot continue, and maybe, by the time 10 years go by and people realize that they really, OFDM wasn't the best choice for some of the new applications. So OFDM clearly has delivered on 4G, right? Pretty much, whatever they said they would do, they did. But now we are pushing the application space a lot more in 5G. So maybe 6G, maybe that is where the next generation will make changes.
Thank you.
So in 5G, where's the multi-hop wireless network positioned? Academia has researched for a long time, but
so that is one of the things where a lot of research happens in academia, and they are great ideas, right? A multi-hop network makes a lot of sense in a lot of applications. But when it comes to actual industrial or commercial deployments, and you look at it and the network context of what it takes to actually deploy a multi-hop or a mesh network, it has never really materialized. So again, right now, 5G does not really, it's still the topology, the architecture is the same in that sense. So there's really no native support for multi-hop networks. But for example, for millimeter wave, right, where you really have a lot more limited connectivity or range per hop, it's not really multi-hop, but you have other ideas where you're trying to stay connected to more than one base station at a time, so handoffs are easier. But true multi-hop, yeah, it's remained an academic research area for a long time.
Yeah, thank you. I think you have a very comprehensive review for 5G network. But what I didn't see is the edge computing, mobile edge. So can you comment on that?
Right. So the mobile edge is, so that is, I look at mobile edge more as an application that's enabled by 5G. So this is what the high bandwidth links is going to enable for you. And a lot of the low latency applications, right, will be enabled by a combination of the mobile edge as well as the inherent low latency of the physical layer as well. So again, it's not something that would be standardized as part of the cellular network. It's definitely an application that gets enabled by everything that 5G will provide for you in terms of bandwidth and latency.
My question is, UMTS technology supports to 5G?
Pardon?
UMTS.
Yes.
Is it supports to 5G?
So it depends on what you mean by supports. It does not support, I mean, 5G is not backward compatible in that sense, right? So you have to get new handsets, you have to have new base stations, you have to have new infrastructure. But your handset can fall back to UMTS if the 5G network is not available, much as we do today too, right? You fall back from 4G to 3G. So in that sense, yes, it's backward compatible, but inherently the architecture, the system is not backward compatible.
You mentioned about different radio access technologies being used maybe for unlicensed spectrum as well. And then the aim is also to have different radio access technologies through slicing in the future. Do you see 3GPP working with different standardization organization, maybe for Wi-Fi or other rats? Is there anything in the plans that 3GPP has?
So the way that traditionally Wi-Fi and 3GPP, they've proceeded on parallel paths. There's a lot of liaisons that happen between these two bodies, but they've never really jointly done anything. And frankly, I don't see that happening either, even in these new spectrum spaces. What I think would be good, and again, this is speaking, just as an academic, as an NSF person, what I think would make a lot of sense is for these two communities to realize that there is more to be gained by sort of looking at what the other system is designing and trying to make coexistence easier. For example, today we have a big problem with LTE and Wi-Fi because these two systems, their preamble structures, their signaling mechanisms, everything is completely different. So now there have been proposals to have a side channel that does coordination. What if we were to design a system for 6 gigahertz that had some of these ideas built in from day one? So that is where I would hope that these two communities go towards. Whether they do or not remains to be seen. Any other questions?
I think there always have a debate between the more theoretical work and more system work, right? So I believe you heard the criticism from both communities. So what's your take, or how are you going to balance the more theoretical work, but hard to implement, and system building work, but perhaps there's no fundamental,
Right.
theoretical contribution there?
I think that's always a very hard evaluation, especially for an organization like NSF, where Historically, we funded much more fundamental theoretical work. And I think that work will continue. For example, if you look at polar codes, right, that came out of very, very fundamental basic information theoretic work. And the professor who developed the codes didn't himself go to standards to push it into it, but there was a company that he aligned with that made that happen. And so that kind of fundamental work to push the boundaries of what you can do is going to continue to be funding. What I think is a more difficult space is, for example, if you want to do something with 5G cellular, right, and you want to do an analytical study. Analysis really works when your assumptions are very simplified and you can get closed form things. The question is, when you do that assumptions, when you abstract out what the real deployment is looking like to a version that you can analyze or even simulate, how much have you lost in that process? So when you come up with a result, how applicable is it when you take it back into the real world? So that is where I think we need to pay a little bit more attention, that when we do the simplification, that we are not changing the problem so much that it's not relevant anymore. And that is the hard space to be in when you're doing this kind of research. Any other questions? Okay, I think we can close the session. We are out of time anyway, so thank you very much.